Hi, everyone. Welcome back to the System Design 101, where we will cover system design basics. Um, Today we're going to look at two concepts they're basically the absolute bedrock of any system you're going to build, right? And these are latency and throughput. And it's kind of funny because, when you first get into systems, you hear these words thrown around constantly, right? People are always like, "Oh, we have a latency issue," or "We need to scale the throughput." And I think people sort of intuitively kind of grasp them a little bit, but they actually get them confused all the time. Like they treat them as if they are the exact same thing, which is, making the system fast, right? You want a fast system, but under the hood, if you sort of squint at what's actually happening, they are measuring two fundamentally totally different things. And actually, in a lot of cases, they trade off against each other, right? Like if you try to optimize one, you sort of end up penalizing the other. So, let's basically just build this up from scratch. Let's build the mental model here. Okay, so let's define them first, in a very simple way. So latency is basically it's the time it takes for one single unit of work to completely finish, right? So if you have a message, it's the exact stopwatch time from when you say go to when the message arrives at the destination. It's a measure of time. Milliseconds, seconds, whatever. Whereas throughput it's a rate, right? It's basically if you look at a given window of time, like a second or a minute or an hour, how many units of work did you manage to push through the system entirely? So it's not about how long one thing took, it's about the total volume of stuff you accomplished over time. Okay, definitions are fine, but I always like to, ground this in something physical because computer networks are basically just plumbing, right? They literally are just pipes sending little pulses of electricity or light. So let's actually think about a physical water pipe, right? Like imagine you have a pipe connecting, let's say, a water tank to your house. What is latency in this pipe? Well, latency is if you drop a single drop of red food coloring into the water at the tank, how long does it take in seconds for that exact red drop to come out of the faucet at your house, right? That's latency. It depends entirely on two things: how long the pipe is, the physical distance, and how fast the water is flowing. Now, what is throughput? Throughput is if I put a giant bucket under the faucet, how many gallons of water fill up that bucket in, let's say, 1 minute, right? How much volume? Now, notice that if I want to increase the throughput, right, I want more gallons per minute, I don't actually have to make the water flow faster. I mean, I could, but the easier thing is I just build a wider pipe, right? If I make the pipe 10 times wider, I get 10 times the throughput. But, and this is the crucial part, the red drop of food coloring doesn't get to the house any faster. The latency is exactly the same, right? Because the pipe is still, 5 miles long, and the water is still moving at the same physical velocity. We just have more of it arriving at the same time.
So, that's that's kind of the absolute basic physical model. But let's look at a more human example because I think it maps better to web servers and databases and the stuff we actually care about in system design. Let's think about a grocery store checkout, right? You go to the grocery store, you have a cart full of groceries. Now, latency in this scenario is you are standing in line, and it's the time it takes for you, specifically, to put your items on the belt, have the cashier, beep, 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 scan them, and you pay and you walk out. Let's say that process takes 5 minutes. Your latency is 5 minutes. Throughput, on the other hand, is the store manager standing up in the front office, looking down at the lanes and saying, how many customers are we processing per hour, right? So let's say there's one cashier and they process one customer every 5 minutes. So the throughput is, 12 customers per hour. Now, let's say the store manager is like, this is unacceptable. Our throughput is too low. We need to process more customers. What do? Well, the easiest thing, and this is basically what we do in system design, right? We just throw hardware at it. The manager just opens up like 3 more checkout lanes, right? So now we have 4 cashiers working in parallel. So what happened to our metrics? Our throughput just went up by 4x, right? We're now processing 48 customers an hour instead of 12. Massive win for throughput. But, and this is the really important thing to internalize, did your latency improve? No, it didn't. You still have to put your items on the belts, the cashier still has to scan them at the exact same human speed, and you still have to swipe your credit card. Your personal experience, the latency of a single request, is completely unchanged. It's still 5 minutes.
And, this is exactly what happens when you have a web server. Let's say you have a Node.js server or a Python server, right? And a user makes an API request, and it takes 100 milliseconds to fetch from the database and return the JSON. If suddenly you get a huge spike in traffic, right, what do? You add more servers behind a load balancer. You go from 1 server to 10 servers. Your throughput capacity goes way up. You can handle thousands of requests per second. But any individual user is still waiting that baseline 100 milliseconds. You haven't sped up the work itself, you've just increased the capacity to do work concurrently. So how do you fix latency in the grocery store, right? Let's say we actually want to bring that 5 minutes down. Well, you have to change the fundamental execution of the task. You give the cashier a faster, barcode scanner, or you introduce self-checkout so people can scan stuff in parallel. Or, right, if we map this back to computers, you optimize your database query. You add an index to the database, right? So instead of doing a full table scan that takes 500 milliseconds, it takes 10 milliseconds. You rewrite the algorithm. You move the server physically closer to the user using an edge network or a CDN, so the speed of light delay is shorter. That's how you attack latency. You have to literally shorten the path or do less work. So, basically, a very quick heuristic I like to use is throughput is usually a money problem, right? Like, if you have low throughput, you can usually just buy more servers, open more lanes, scale horizontally. Boom, solved. Latency, on the other hand, is an engineering problem, right? Or sometimes a literal physics problem. Like, you can't bribe the speed of light. If a packet has to go from, Tokyo to New York, it's going to take roughly, maybe 80 to 100 milliseconds minimum, just bouncing through fiber optic cables. You can't buy a wider cable to make the light travel faster. The speed of light is a hard stop. So you have to redesign your system, maybe replicate your database to Tokyo, so the packet doesn't have to travel as far.
Okay, so let me tell you my absolutely favorite sort of extreme, bizarre example of latency versus throughput, because I think it really pushes the mental model to the absolute limit. And this is a very famous, classic computer science example. I think it comes from an old textbook. Imagine you need to transfer a massive amount of data. Let's say an entire data center's worth of backups, right? A petabyte of data, 1,000 terabytes, and you need to get it from New York to San Francisco. Now, you could try to send this over the internet, and let's say you have a really good, gigabit fiber connection. It's blazing fast, right? The latency of a single packet going from New York to SF is amazing, right? Like 60 milliseconds. So the latency is super low, but the throughput of that pipe is, 1 gigabit per second, which means to send a whole petabyte, if you do the math, it would literally take you over 100 days of just continuous uploading. So what is the alternative? Well, you take all those hard drives, right? All, let's say 100 giant hard drives. You put them in cardboard boxes, you load them into the back of a station wagon, and you just physically drive the car from New York to San Francisco. Let's analyze the station wagon as a computer network. What is the latency? The latency is atrocious. It's terrible. It takes like 4 or 5 days for the car to drive across the country, right? A packet over fiber takes 60 milliseconds. The car takes 5 days. You send 1 byte of data in that car, it takes 5 days to arrive. But what is the throughput? The car arrives on day 5 and suddenly, boom, 1 petabyte of data arrives all at the exact same second. If you divide 1 petabyte by 5 days, the throughput is like 20 gigabits per second, right? It completely crushes the internet connection. So the station wagon has incredibly high throughput, but horribly high latency. And, it sounds like a joke, but Amazon actually literally does this. AWS has a service called Snowmobile, right? It's an 18-wheeler semi-truck that they drive to your company, they plug it into your data center, suck down 100 petabytes of data, and physically drive it to an AWS region. Because when the data gets that big, the physical truck has more throughput than the entire internet. It's just amazing to think about. Okay, so let's pivot a little bit. We've sort of established what these things are, right? But the really interesting system design stuff, the stuff you're actually going to have to architect, is where these two things directly compete with each other, where you have to sacrifice one to get the other. And the absolute most common way this shows up in system design is batching. Let's look at batching. Okay, imagine you have a web server and it receives analytics events, right? Let's say every time a user clicks a button on your website, it sends a little tiny JSON payload to your server. User clicked button, and your server needs to save this to a database on disk. Now, disk writes are, relatively slow, right? So if you take every single click the millisecond it comes in and you instantly write it to the disk, your latency is incredible, right? The exact moment the click arrives, it's saved. That's, maybe a 5 millisecond latency. But what about your throughput? The problem is, doing a million tiny, individual, separate disk writes puts massive strain on the system. The disk has overhead, the database has transaction overhead, the CPU spends all its time context switching. And eventually, if you get too many clicks, the disk just locks up. It can't handle it. The throughput hits a ceiling really fast. So as a systems engineer, what do? You say, okay, we're going to introduce batching. Instead of writing to the disk immediately, you take the incoming clicks and you just drop them into a little queue in memory, right? A tiny little buffer, and you wait. You let the clicks pile up. You wait until you have, say, 1,000 clicks, or maybe you just wait for exactly 1 full second, and then you take that whole giant chunk of 1,000 clicks and you do one big single write operation to the disk. What just happened to our metrics? Well, our throughput went through the roof because disks love big sequential writes. They hate tiny random writes, right? It's much more efficient to write one big block of data than 1,000 tiny blocks. So your system can suddenly handle, hundreds of thousands of requests per second. Your throughput scales massively. But what happened to our latency? Our latency took a hit. It got strictly worse. Because if you are the very first click that arrives in that empty buffer, right, you don't get saved to disk immediately. You have to sit there, waiting in memory for a whole second, waiting for the rest of the batch to fill up. So your latency went from 5 milliseconds to basically 1,000 milliseconds. And, this is the fundamental tension. We intentionally made the latency worse. We intentionally slowed down the individual request to protect the whole system and allow it to process more volume over time. And you'll see this everywhere, right? Like TCP does this under the hood with Nagel's algorithm, right? It clumps small packets together before sending them over the network.
Kafka is like entirely built around this idea. You produce a message, Kafka waits to batch it up and then flushes it to disk. And so when you are designing a system, right, you have to ask yourself what actually matters for this specific product? What is the user experiencing? Let's contrast two completely different applications. A multiplayer, competitive first-person shooter game like Counter-Strike or Valorant versus, let's say, Netflix, right? Streaming a 4K movie. If you are playing a multiplayer game, what matters? Latency is literally everything, right? If you press the mouse button to shoot, you need that packet to get to the server and back as fast as humanly, physically possible. If it takes 200 milliseconds, the game feels laggy, it feels awful, you die, right? You just hate the experience. But the game doesn't actually need much throughput at all. Like, what is it actually sending? It's sending, an XY coordinate, a button click, a rotation vector. It's like a few bytes. It's a tiny trickle of data, right? So for gaming, you architect the whole system, you optimize the network protocols, you probably use UDP instead of TCP, all to shave off like 3 milliseconds of latency. You completely sacrifice throughput. You don't care about data guarantees as much. You just want it fast. Now, flip it around. Look at Netflix, right? If you are streaming a 4K movie, you need massive throughput. You need megabits and megabits of data constantly pouring into your TV. If your throughput drops, the video degrades to 480p or it stops and buffers, right? It's ruined. But what about latency? Does latency matter for Netflix? Honestly, not really at all. If you click play on a movie and the server takes, an entire 2 seconds to grab the file and start sending the first bytes, you don't care. You're sitting on your couch with popcorn. A 2-second delay before the movie starts is completely fine. And once the movie is playing, Netflix keeps a huge buffer in memory on your TV, right? Like a 30-second buffer. So if a few network packets are late, if the latency fluctuates wildly, you never even see it. The buffer absorbs it. So Netflix optimizes strictly for throughput. They use big CDNs, big hard drives, massive pipes. And, it's this duality that makes system design so interesting, because there's never a perfect system that just maximizes both infinitely, right? You're always turning these knobs. Like, if we sort of zoom back out to a generic web application architecture, let's say you're building Twitter or something, you have a user loading their timeline. You want low latency because the user is staring at a white screen waiting for the tweets to appear, right? You want it under, say, 200 milliseconds. So what do? You introduce a cache, like Redis or memcached, right? What is a cache doing mentally in our framework? It's a latency optimization. You're saying going all the way to the main database takes too long. The path is too long. So you take the data and you move it physically and logically closer to the application server. You store it in RAM instead of disk. You've shortened the pipe, right? The latency drops. But simultaneously, you have a huge fire hose of incoming tweets. People are tweeting all the time. That's a throughput problem. So for that part of the system, you introduce a message queue, like Kafka or RabbitMQ. You let the tweets pile up, and you have a bunch of background worker machines churning through them in parallel. And so you basically end up splitting your architecture. You have a read path, which is highly optimized for ultra-low latency using caches, and you have a write path, which is highly optimized for ultra-high throughput using queues and batching. And honestly, if you really deeply understand just these two concepts and you know how to sort of sniff out, okay, is this a latency bottleneck or a throughput bottleneck, you can navigate almost any system design interview, right? Because whenever an interviewer says, okay, our system is slow, your immediate follow-up question should always be, wait, what do you mean by slow? Is the individual request taking too long? Or is our overall capacity maxing out and we're dropping requests? Because the tools you pull out of your toolbox to fix it are entirely different, right? Like, again, throughput, buy more boxes, parallelize, batch; latency, buy better algorithms, move data closer, cache, index. So, basically, yeah, just remember the grocery store. Remember the station wagon full of tapes. Those are your mental anchors, and whenever you look at an architecture diagram, just trace a single request to find the latency, and then imagine a million requests at once to find the throughput bottlenecks. All right, so let's stop there for today, and next time we'll sort of plug these concepts into actual database replication and see how it breaks down. Thanks.